plot out an instance of that random process starting at time 0. So at 0, let's say I flip heads. Then what's the value of the function at that time? 0. What if I flip tails?
0.
It's t, which is 0, so it's still 0. So it doesn't matter what I do here, it's always 0. At time 1, let's say I flip tails, plus 1. At time 2, let's say I flip heads, so that's 0. At time 3, let's say I flip heads, so that's 0. At time 4, let's say I flip, actually let me write this down. So let's say here I flip tails, here tails, heads, tails, and heads, heads, tails. What's the value of the function at this time 4? 4. It's 4. Heads, tails, tails. So what's the value here? 0. Value here? 6. Value here? 7. So in other words, as I go along, the amplitude will increase whenever I have a tail. Okay, so that's interesting from the perspective of mean and variance because it means that because it illustrates the fact that mean and variance are a function of time. So mean and variance can be functions of time. So let's take this example. What is the expected value of x of 1? Well, let's look at what x of 1 can possibly be. So x of 1 is 0 if I have heads. And what is it if I have tails?
1.
It's 1. So this is a fair coin, so the probability of each 1/2. So the expected value of x1 is equal to 0 times 1/2 plus 1 times 1/2, which is 1/2. Let's try that again for x equals 2. What's the expected value of x equals 2? It should be 1. Why? Because if I have heads, it's 0, that's probably 1/2. And if it's tails, what's the value? It's 2, that's probably 1/2, it's 1. So more generally, what's the expected value of x of t? It's t over 2. Because I have 0, probably 1/2, and t, probably 1/2, which is t over 2. So the mean of this random process is a function of time. So depending on when I look at the random process, its mean will be different. Similarly, the variance. The mean of x of t is equal to t over 2. The variance of x of t is equal to, I'm going to use the trick I showed you last time. This is expected value x of t squared minus the mean squared. Let me write that less confusingly. Okay, what's the expected value of x of t squared? This is 1/2 times, if it's heads, it's the outcome of the experiment x of t is 0 squared plus 1/2 times if it's tails, the outcome is t, so that's t squared. Minus mu of x, which is t over 2. What's t over 2 squared?
T squared.
T squared over 4. So we get t squared over 2 minus t squared over 4, which is what?
T squared.
T squared over 4. So we have that mean and variance are both functions of time. Okay, so far it's not too different from just normal random variables, it's just the sequence of them. Now, here's one thing that's new. That is autocorrelation. So first, let's talk about correlation, just plain correlation. So let's say I have, a random process, x of 1. Let's take its value at time 1, and its value at time 4, or something. It doesn't really matter what numbers I pick here. And let's say I want to know how correlated are those values? Let's start out by saying the mean of this process is 0 for all time. So what I want to know is how correlated is the process at time 1 as compared to time 4. So for instance, if I look at all the possible instances of this process, if I have a value of, let's say, +1 here at time 1, and then I look at time 4, I want to know, is it close to +1? Like, for instance, is it just a little more, like plus 1.2 or plus 0.8 or something like that? In that case, these would be highly correlated. In other words, if I know what the random process is at this time, it really tells me something about where it is here, so that allows me to predict. Or are they highly uncorrelated? In other words, if it's +1 here, this could be anything. And it really makes no difference knowing what I have at time 1. So what I'm looking for is a measure between time 1 and time 4 of how correlated these two values are. So as a candidate for a correlation measure, let's try this. What's the expected value of x of 1 times x of 4? So I'm not going to say, this isn't the same random process that we've had in the examples, and I'm not going to say whether these values are independent or not, because the whole point of the correlation measure is it's going to tell us how independent they are. But let's say first off that they are independent.